Hi everyone. Today's lesson is the last lesson for chapter 14, thermophysics. We'll be looking at specific latent heat, and in particular, we're going to even define the specific latent heat of fusion, a specific latent heat of vaporization. We're going to look at an experiment to determine it, fusion and vaporization as well, and techniques and procedures used to determine the specific latent heat of a solid and a liquid. So what we have is firstly, what is specific latent heat? Firstly, we look at what the actual words mean. Specific refers to 1 kilogram of mass, so that's what we mean by specific. Latent means hidden, and obviously because it's heat that you can't measure with thermometer, that's why they call it hidden. So specific latent heat of a substance is the energy required to change the phase per unit mass while at constant temperature. And if you look at the definition, is the energy required to change the phase per unit mass. So energy per unit mass. We represent latent heat of fusion or vaporization with an L, but they will have subscripts because they're different and they also have different value. E stands for the energy supplied to change the phase of the mass, or the energy released sometimes. If you're going from a gas to a liquid and a liquid to a solid. And there are two forms, like I said, the specific latent heat of fusion. You can see here that is L with a subscript of F to stand for fusion. So I'll actually discuss it a bit more in detail later. And then the specific latent heat of vaporization, which is represented with a subscript lower V. So it's from liquid to gas state. That's the difference between them. So in order for us to go from solid to a liquid or a liquid to a gas, energy needs to be supplied. That's very important. Remember that you have to supply energy to break the attractive electrostatic forces between the particles, so atoms or molecules or ions in a substance. So you have to supply energy to overcome them. And if you're going from a liquid to a solid or a gas to a liquid, energy is taken from the material and is released to the surroundings. That's because obviously you have the bonds forming, which have a negative energy. So as a quick summary, and if you have to supply energy to the system, you say that work is done on the system, on the material or the system. So work done is on the work is done on the material. In this case, work is done by the material. The other point I wanted to mention here was regarding how the internal energy of the system will be affected. So what we have is the internal energy, if you remember, with the kinetic energy, which will remain the same. So kinetic energy remains the same. As you see from the definition, for latent heat is defined as the energy required per unit mass at a constant temperature. You can't forget that part in definitions because you won't get the marks. It has to be at a constant temperature. So if it's at a constant temperature, the kinetic energy of the system will remain the same. However, the potential energy will change So if you're going from a solid to a liquid or a liquid to a gas, the potential energy increases. However, if you're going from a liquid to a solid or a gas to a liquid, the change is the opposite. So potential energy decreases. That means that the internal energy will increase, obviously, since kinetic energy remains the same, but potential energy changes, and in this case, the internal energy will decrease. So energy will be released to the surroundings. So the actual, let's say you had water molecules freezing, they will release the energy to the surroundings. So the internal energy of the liquid going to a solid will decrease, and it will go instead to the surroundings, so whatever is in contact with it. Okay, so now what is a specific latent heat of fusion exactly? The definition is here. It's the amount of energy required to change the phase of 1 kilogram of a substance from a solid to a liquid at a constant temperature. It could also be from a liquid to a solid, so either way around it works. So this is the definition for it. So basically, it can only happen at its melting point or freezing point. So going from a solid to a liquid, we talk about melting point. If it's going from a liquid to a solid, is the freezing point. So the energy transferred increases the internal energy, but there is no temperature increase. It's very, very important. To investigate this change, we can use a heating circuit like we used before with a specific capacity. So we'll need the equipment shown in the diagram and a few more things actually than that. You'll definitely need a thermometer. You will also need an electric heater. The heater has to be connected to a circuit. Now the circuit should include a voltmeter in parallel, so you can measure the voltage, and an ammeter to measure the current going through it. It could be a cell, it could be a power supply, which is using this symbol, whatever it is. And so what you have here, you need to have the known mass of the ice that you use. So basically you put ice in a funnel and you measure its mass. Well, actually you don't need to measure its mass, but it should be constant because you will need a second setup which has another funnel with ice. Funnel with ice inside of it and the heater. In this we call it the control setup because it won't be connected to power supply. It needs to be simply just there for a reference, and I'll explain it in a second, you'll understand it. So what you have is that you turn on the system. It is ice, so it will usually start melting. And you need a thermometer to record the temperature. You need the heater to heat the ice, so you can be able to measure the energy you're providing. Remember that the energy supplied should be part of the equation. So if I want to measure the latent heat of fusion of water or any other substance, I need it to be in solid form first, so ice. And since I'm trying to measure this experimentally, my equation will be E divided by M. So energy measured in joules divided by the mass of the ice. Well, the mass of the melted ice, actually. So we need a control setup to remove that any ice that melts not due to the heat, that melts under normal conditions. So the steps that you should take is that you should measure the mass of ice, so you can keep both of them, even the control experiment here. You need to know the mass of the ice. It should be equal in both the funnels. Get the power reading from your ammeter and voltmeter. So you know that power is equal to voltage times current. You will also wait until the water first starts dripping from the funnel into the beaker, so you know that it's at the temperature where it starts melting. So basically, you will know exactly when it starts melting. And then you start the heater, and obviously you need a stopwatch to measure a fixed amount of time. So let's say 15 minutes or 20 minutes. The longer the time, the better, because it will actually decrease your uncertainty in the measurement of time, which is good. So you start the heater, wait 15 minutes or 20, and then you switch it off. And then you need to measure the mass from both beakers. So for example, if the beaker, after you finish the experiment, here you measure the mass to be, let's say 100 grams, and here it was 20 grams. Now here, remember, we didn't provide any electricity, we didn't heat it with any electrical elements at all. So those 20 grams will be basically just ice that melted naturally due to the environment, so due to the surroundings, due to the temperature of the surroundings. But in this case, we will know that the ice melted is from the surroundings and the electrical heater within the system. So at least we will know exactly how much energy was provided directly to melt the 80 grams of ice into water. So you just subtract the two values to get the amount of ice that has been melted due to the energy we provided. This makes the measurement more accurate. Otherwise, you will have this extra 20 grams that you didn't account for, and it will basically shift your value by a different amount. It will give you a higher, so you look at it here, so it will give you a lower value, latent heat of fusion, because you will divide it by a higher number otherwise. So to avoid that mistake, we use a control setup. I wanted to bring your attention to this diagram. Now this diagram shows temperature against time of heating up a solid, for example. So in this one is water, so it's the temperature of H2O as you provide heat during the time. What you have is the beginning from, if you had ice at minus 40 degrees, for example, and you start heating it up, the temperature will be increasing until it reaches its melting point. And then you can see that there's a plateau here, there's no temperature increase, so all the extra energy I'm providing is used to break the attractive forces. So I am giving that extra energy to break those attractive forces between the particles. Once and at that phase, as you can see from here, it's both ice and water during that time. But then when it reaches this point here, let me use a different color maybe. When it reaches this point here, you can see that as I continue heating it up, the temperature starts increasing again, while it's in its liquid state, so water. Then we reach once again, so this is where we have the latent heat of fusion, and we can use the equation E is equal to M times L to calculate the energy provided. Here we can use MC delta theta, to calculate the energy provided while the temperature is changing. Here again, you can use the same equation because the temperature is changing. You can't use it here because there's no temperature changing. There's a phase change only. That's why we call it latent heat of fusion, because it's a hidden heat, a hidden energy change that we can't measure while just taking the temperature change basically, which there is no temperature change. And then we go to the other point here, which is the latent heat of vaporization. So we have the energy provided while the liquid is changing into gas. So, and you can see the picture. It shows that there's liquid and gas at the same time, and then eventually when it all turns into gas, you reach this point where you have an increase in temperature of the gas, and it's in the gaseous state only. And you can calculate it once again. You can calculate the energy needed to reach that point using this equation. And we will come back to this at the end with an example. Okay, so specific latent heat of vaporization. By the way, the specific latent heat has the same definition. It's just when you talk about fusion of or vaporization, specifically you have to just state what phase goes to what phase. So here's the same definition. It's the amount of energy required to change the phase of 1 kilogram of substance from a liquid to a gas at a constant temperature, or from a gas to a liquid, depending on what's going on in the question, what the question is specifically asking you. So that happens at the boiling point or the condensation point. And you should know, so you need to actually remember that the change phase can occur the other way around, so boiling point or condensing point. And at this point, it's a good opportunity to talk about which of the two latent heats of fusion is usually higher and why, because you will need to know about that. So what we have is latent heat of vaporization is always bigger than the latent heat of fusion for most substances. Now that difference has to do a lot with the potential energy. So if you consider the potential energy between a solid to a liquid, so the difference between the two potential energies, and the potential energy between a liquid and a gas. Now, solids and liquids have quite high attractive forces between them. So that means that the potential energy required for both of them to, overcome those electrostatic forces is quite small, the difference between them, because they both have quite high electrostatic forces. So there's a low difference in potential energy between those two states. But when it comes to a liquid and a gas, since the gas particles are so far away, they experience nearly no potential, no electrostatic attractive forces, which means the potential energy is 0 joules. I already mentioned that in the last video. Is the part that confuses all of the people, is that it has the highest potential energy because it's just 0. But the liquid has potential energy, so that means that it will have the biggest difference in potential energy between going from a liquid to a gas. So that means that the internal energy going from a liquid to the gas is bigger than the difference, that's supposed to be difference, sorry, in internal energy between a liquid and a solid. And last point to mention, so you don't forget, is to remember that the going from a liquid to a solid, the energy is given to the surroundings instead of taken from a different source. It's just all about the right way. So this experiment is a little bit more complicated than the first one. In this case, we have this setup here. It includes a weird setup at the top, like this, and I'll go into it in a second. And that setup is connected to a condenser So basically condenser has water that's used to cool down vapor that passes through this middle tube here, the purple tube. And obviously when you cool down a vapor, it turns into liquid so that you can collect it and measure its mass. What this setup has here, you have your heater connected firstly. So this is the heater here, the one that's pointing, the little line is pointing at. And this is also connected to your circuit so that you need to know the voltage with a voltmeter, an ammeter, and an ammeter, and then it's connected to a power source as well. So the heater is used to heat up a liquid. Remember, latent heat of vaporization measures the how much energy is required to change a substance from liquid to gas. Hence why we have a liquid here. Liquid there is labeled. Once you start heating the liquid at its boiling temperature, it will start rising. So imagine this is the liquid rising, and there are these little gaps here you can see that allow the water or gas vapor, whatever it is, to come out. So it will be in this section, in the outer flask, contained within the outer flask. And as it passes through, so as the vapor goes to the condenser, which is here basically, so this is the part where it goes to the condenser, it will cool it down and it will be collected. So the steps to this experiment is to heat the substance to the boiling point, allow the vapor to pass, the vapor will pass through the holes, and then it will pass through the condenser where it will cool back to the liquid form. The vapor is collected for a fixed amount of time, T. Like I said before, the longer it is, the better. So 15 to 20 minutes is perfect. And what we will do is then take this flask and measure its mass. We're going to call it mass 1. Now we know that the energy that we supply electrically should be equal to the energy of the phase change plus the energy given to the surroundings, because we can't really insulate this setup very well. It's hard to insulate to prevent any energy from escaping. So to minimize any mistakes in the experiment, we should really try and make a second measurement. So this is an expression. This here is an expression of this equation that I said above, because energy is conserved. It cannot, be created or destroyed. So basically what I'm saying is that the energy I gave to heat it will go into changing the phase, but also some escapes. So we need to account for that. Hence why we need to repeat it again. So we're going to repeat the experiment, and this time use a different amount of power. So change the voltage and current, which we're going to call, before I actually continue, just because I didn't make it very explicit, energy supplied electrically is power is equal to VI. But since E is equal to ML, since I'm taking into account the time as well that it took, power is also energy divided by time. So if I times both sides of the equation, then I can get the energy. So it will be energy is power times time. Energy is IVT. So then I have this expression as IVT is equal to M times L. Okay, so moving on. This is my first expression, like I said. It applies. And then I repeat the experiment for different value of V and different value of I, current, potential difference in current. I do another expression again, because obviously when you repeat the experiment, you still have some energy being wasted to the surroundings. And then I will rearrange my equations to make Q the subject in both cases. As you can see, I've done it here. I equated them because both of them come out to look quite similar. Then I will take the same expressions on the same side so I can simplify them. And you will end up with this expression. Since you already know, since you will be able to already have measured your voltage in both cases, so in current, you'll have these values. You already have your fixed time, which you will use a stopwatch for, and you also need a scale to measure the mass of the collected water. Remember that when you collect the mass of water in, or any substance in a flask or any container or beaker, you always need to make sure that you subtract the actual mass of the beaker as well, so that you can get just simply the mass of the water or liquid in the container. Now in exams, you might not only just be asked to calculate the energy required to change phase, or just the energy to increase the temperature of something, of a substance. You might be asked to do calculation of all of it together. So it's very important just to go through this example question. So it says to calculate the energy required to boil. So that's a key term, by the way. You need to be able to understand that. So ice, 2 kilograms of ice. So boiling refers to reaching 100 degrees Celsius, which you should know this value. So it gives us the mass of the substance that we need to boil. That was initially at minus 40 degrees Celsius. So the starting temperature is minus 40 degrees Celsius. And to determine the percentage of this energy required to change the phase of water from liquid to gas. So it wants us to determine the percentage of the energy from that compared to the liquid to gas. This means that we need the energy of the latent heat of vaporization, because it's from liquid to gas. So let's start first with the energy required to boil 2 kilograms of ice at minus 40 degrees. That was initially at minus 40 degrees. So we have the energy that we need to calculate, but we also need to break it down to the expressions that we require. So first things, we need, obviously, for us to be able to boil the ice that's at minus 40, it will first have to increase the temperature from minus 40 degrees to 0 degrees, where it is a melting point. So we have that temperature change. So we have to use E is equal to MC, change in temperature from from actually minus 40 degrees to 0 degrees, plus the energy while it's at 0 degrees to change phase, right? So the latent heat of fusion, because we're going from a solid to a liquid. Then we need the energy required to take it from from 0 degrees Celsius to 100 degrees Celsius, which is the temperature at which it boils. So we need MC delta theta. Here is from 0 to 100 degrees Celsius. And then the energy while it's at 100 degrees Celsius, where it's the boiling point, where we have a phase change from liquid to gas. So that will be MLV. So the latent heat of vaporization. So then now I just need to put my numbers in. I know that it's 2 kilograms for the first expression times the specific heat capacity of ice, which is this much, because this is where it's ice. This is when it's water. sees water. We have 2 times 2 times 10 to the 3 times, since the temperature goes from minus 40 to 0, the change in temperature is just 40, plus 2 times the latent heat of fusion for water, which is 3.3 times 10 to the 5, plus we go to this expression now, 2 times specific heat capacity of water is 4,200 times the change in temperature, so this is we're going from 0 to 100, that's 100, plus 2 times the specific latent heat of vaporization, which is 2.26 times 10 to the 6. And then when you do the calculation, it will come to about 5.58 times 10 to the 6 joules, or roughly 5.6, since the lowest number of significant figures is given to 2 megajoules. And then we do a calculation for the energy required to change it from a liquid to a gas, so we can get the percentage difference. So that will be just this number here. So E is equal to mLV, which comes to about 4.52 megajoules. I will actually leave my answer to this format because I can round it up at the end when I'm done with my calculations, and I just need to find the percentage of that. So the percentage difference, the percentage of energy going from a liquid to gas compared to the whole change is going to be 4.52 megajoules divided by 5.58 megajoules. I left it as megajoules because even if you wrote times 10 to the 6, you will cancel them out anyway. Times up by 100, that will give you about 81%. As you can see that about 4/5, more than 4/5 of the energy was actually required to change the liquid to a gas, compared to even increasing the temperature of the water and the whole process completely together. So you can see that most of the energy is required to change a liquid to a gas from this question. Hope this helped, and if you have any questions, please do write them down so we can answer them in lesson.